Hello everyone. In this brief video I want to talk about the static stability of legged robots. So if you have a legged robot like a humanoid all the way to uh, basically hexapods that they have 6 legs all the way up, under what condition they are stable under static condition. And static here means they don't move, or if they are moving it's extremely slow. So how can we make sure that how many of the legs we can lift up at any time point, given the load distribution on the robot or the mass of it alone, or if they're carrying something, and make sure that the robot is not going to tip over and fall. So if the robot has legs on a flat train, on a flat surface, and the surface has friction, the static stability is quite simple. So you connect the points of contact of the legs that are on the train or on the ground. You connect all of those contact points together and form what we call a polygon of support, or support polygon. And you also project the centroid of the total robot onto the horizontal plane, right, onto the flat train. You project it down, and as long as the centroid is inside that convex hole, inside that polygon of support, then it is stable. So you see, what matters is really the x and y position of the centroid, right? So if I have these 3 coordinates here, right, x, y, and z, all that matters are x and y components of the centroid, not z. So if this is a taller robot or a little bit kind of shorter robot in height, it is not going to affect the stability, okay? And again, this is under static load, and that is only under mass. Now, if, of course, if there is some wind or any lateral force on the robot other than mg, then if you want the robot to keep its static equilibrium, clearly if the robot is basically taller, you have a smaller chance of stability. It can roll in this direction. Okay, so here by static stability we are only focusing on gravity really, okay? And we are not assuming that there is any lateral force or anything applied on the robot. Clearly, if your robot is in an outside train and there is some wind or so, you have to make sure that there is no roll or no pitch or nothing, okay? So we are talking about all of those, and we can talk about them in a separate video. Here, we just make life simple by just focusing on gravity alone, okay? And let's say this is the direction that the robot, this hexapod, is moving this way, okay? Now, let's talk about a couple of things and then I come back here. So for this robot here that you see, it has 3 legs, you can form this triangle, and as long as the centroid is inside of it, this is stable. But if the robot moves the major part of its mass outside this triangle, so now if you connect these and form this triangle, if this head, which is the biggest part of this robot, moves and the centroid comes here outside this triangle, now this guy is gonna definitely is gonna roll this way and it is gonna fall, right? So you can see this is quite a bit simple. As long as you know the mass distribution of the robot at any point based on the kind of motion that it has, and as long as you know which legs are in contact with the ground, it might not be super daunting, and you might even come up with some margins of stability. So what is margin of stability? In this case here, when you only have these 3 legs, right, and you have this basically what we call the triangle here for the support, then if this point here is the centroid, you find the distances of the centroid to the 3 edges. You find these normal distances of the centroid to these 3 edges, D1, D2, and D3. Clearly, if any of these distances becomes 0, you are at the verge of becoming unstable. And if it becomes negative, clearly unstable, right? So we need all these three numbers to be positive. And the bigger they are, the better you are stable. I mean, like, if it comes right here, still what? Let me draw it right next to it. If it comes here, it is still stable, but now it is very dangerously close to this bottom edge here. So now you see that this distance is becoming very small, so there is a chance of robot rolling this way. So you want all these three distances to be large enough, or basically you want the minimum of them to be large enough. So you can define the minimum of these three distances as what? As the stability margin. Okay, the bigger it is, the bigger the stability. The smaller it is, the smaller the stability. And when it becomes 0, now you're about to become unstable. Okay, so this is called stability margin. And if you want to take into consideration the direction of motion, then instead of projecting this or finding the distances, the normal distances of centroid to these three edges, what you can do is just in the direction of motion, you find the distances of the centroid to what? To whatever edges that are on the way of motion. So you draw this line parallel to the direction of motion. Wherever it intersects the sides of this triangle, you find these two distances, D1 and D2, and now the minimum of them will be what we call the longitude or longitudinal stability margin. So this is the stability margin for the direction of motion. So basically, as this robot goes forward, right, you don't want it to what? Tip over in the direction of motion or goes backward this way. You don't care about these other rolls. If it rolls to the side like this or this, you don't care about these. You only care about basically tipping over in the direction of motion or backwards. Okay, so then you can define this as longitude stability margin as well. Now, by the way, before I move on, let me just emphasize that the pictures and equations are here mostly taken from this paper, Testing Static Equilibrium for Legged Robots by T. Brettel, okay, which is a beautiful paper, and I just mentioned a little bit part of it here, not all of it. Now, here we made some big assumptions. The assumptions was the train is flat, it has friction, and of course there is no lateral force. So if we just violate one of them, which is the most common one, because most surfaces do have friction, and if it's indoor, then probably we do not have lateral forces, right? But we can always have a robot that is walking not on a flat surface. It is climbing up or down stairs, or it is going on surfaces that are what? It is that are not all flat. So one leg could be here, one leg could be here, one leg could be here. Now, not all of the legs are on flat surfaces. This leg here is on a slope. So if the train is not flat, calculations are not as easy, okay? So here, let's say the train is not flat, still has friction, and still no lateral force. Now, as I'm gonna just show you with pictures, the calculations for the shape of the support region is not as simple. And in this paper, it is shown that just connecting these 3 points and coming up with this convex hole or polygon is not enough. So this paper shows that the shape of the support region could actually not be necessarily a polygon. It could be some kind of projection, okay? And it can be something like this, kind of like, it's not an ellipse, but something like that, okay? And it shows that the shape of the region, as long as you see here, this support contacts are not flat, instead of being this big triangle, it's a smaller subregion of that, and the boundaries of that are not flat, it's kind of curved. While again here, when they are flat, of course, you can go with the triangle. So pay attention that if your legs are not flat surfaces, the support region is not going to be a convex hull. It's going to be a sub-region of that. So what are the equations that you need for stability here? So here we are looking at the three-leg robot again. And the location of the centroid, we show it with C, which can have three parameters, C1, C2, C3, X, Y, and Z of it. The normal forces at this contact points are shown by X1 vector, X2 vector, and X3 vector. And the locations of contacts are shown by R1, R2, and R3. So these are the locations of the contact points. C, as I said, is the location of the centroid, the vector for it. X's are the contact forces, and then the local normals at those contact points are shown by V1, V2, and V3 here. So for static stability, we need some of the forces to be equal to 0. And here again, the only forces we have are these Xi's and Mg. Okay, so sum of all of these should be 0. And clearly these Xi's are not all vertical direction. Then sum of the moments could be 0 about, let's say, origin here. So wherever origin is, let's say origin is here, for instance, or here. Then sum of the total moments about the origin should be equal to 0. And origin is again this point. So here you have to find all the moments. So the moments of the forces is R, their R's cross their forces, R cross X. And for this guy, it's the vector of position of it, C cross the mg force. So this mg is in the negative E3 direction. So if I want to write it as a vector, I have to say times negative E3. I got these equations directly from the paper. They are written like this. So you see, these are static stability, and there is some inequality here. What is the inequality? Let me show you. As I said, the V's are the local normals. So if I want these forces X to be what? The reaction forces. If I want to decompose these reaction forces into a normal component and into a tangential component, right? Because wherever you have this block on the surface, you know, you have a friction component and you have a normal component. So your total reaction is basically what? This diagonal one, huh? So this is your N, this is your F, this is your total reaction R here, which you showed with X instead. So here, if I want this N and if I want this F, and here V is this direction, then I have to find these cosine and sine components. But here, these are 3D, so there are 3 angles. And if you want to find the components of this R, which again here we show with X, in the normal direction along V and along perpendicular to V, we can, using linear algebra, show that the normal component of the forces X in the direction of V, basically, right, the normals, or in the direction of V, is going to be VI transpose XVI, right? Why? Because VI transpose X is to project X along V. That is a component, that is a scalar, and then you multiply it by V, that is going to be the vector. And then I minus VV transpose times XI, this is the tangential component. So now it says the tangential component should be less than or equal the normal component times mu, and this mu is mu s. And that is what we had in Coulombic friction. You know, the static friction is less than or equal mu s times n. So you see the tangential component is less than mu s times normal component, and this is exactly this one here. Okay, this is like your n, and this is like your f. So this is from the Coulombic friction. So we have to find here, what are the unknowns? The unknowns are the components of x and what? The components of the centroid, right? If the r's are given. if we know the R's, then we have to have centroid in such a location and these forces to be such that these equations are all satisfied. Two of them are equalities, one of them is inequality. And here I don't go further into details of that, but if you follow this paper, they offered an iterative algorithm to find the shape of the support region based on solving these equations for x's and c's. And they showed that basically if this is, let's say here is for a four-leg, this picture is for a four-leg robot, they found basically their algorithm as it iterates from the first iteration to the last one, it basically finds an inner region, inner support region, and then an outer support region. And the actual support region here is going to be between this inner and outer, okay, this red one. So outer is here shaded, the inner is not shaded, and the dashed line is the boundary of the actual y. And as the algorithm converges, you see that the number of vertices of the inner one is increasing, and ultimately the difference between inner and outer becomes so minimal that basically they can both converge to what? To the actual support region. And you see that the shape of the support region here is what? As you can see, this kind of egg-shaped. It's not really a four-sided shape, okay? It's just that. So here for this triangle, if you repeat that, you can see that you get kind of this region, okay? And it depends on all of the slopes and everything. Okay, it depends on V's. So here, not only you have R's, you also need to have what? You also need to have these VI's. Okay, and based on what you have for I's and V's, which you see they show themselves in your equations, right? The V's show themselves here, the R shows themselves here, then you get different solutions for x's and for the coordinates of c that are going to be statically stable, and it tells you that, hey, in this region, as long as the horizontal position of centroid is, I'm stable. Okay, it gives you the feasible region. So if you want to look at their algorithm, you can refer to the paper. I'm not going to describe that because it's quite a bit complicated and it takes a lot of time. But in general, if the terrain is flat, we go with the support polygon, centroid is inside. If the terrain is not flat, you can refer to this paper and see that it is going to be smaller than that convex hull that you think it is, and it is more involved. So hopefully this lecture was useful to you. You also learned something about stability margins. And I will see you in the next lecture. Thank you.